Very much for having me. I think this is a really great sort of topic for a workshop like this. Perfect.
That side is, no, it's fine. It's fine. That side as well.
Really great topic for a workshop like that. So thank you very much for inviting me. There's a lot of work here that is very close to my heart. This is going to go on for a while. This is great. Okay. There's a lot of sort of work here that is very close to my heart in terms of particularly what the previous speaker was talking about in terms of learning representations for this sort of work. And today I'd like to take you a little bit on a journey that some of my students have been on together with me and my collaborator Bernhard Schürkopf, in the context of what we come to think of as modular world models. And ultimately I'll be talking about things like causally inspired inductive biases to end up with sort of modular world models that are composed of mechanisms that are ultimately reusable. We are fairly early on in that journey, so we'll talk about the different type of data sets that we're usually used to. But I promise that towards the very end we'll get back to something that we recognize as roboticists and that actually adds value to what we do in our everyday sort of world. Okay, so we've already talked about and heard about foundation models quite a bit. We've come to appreciate that we can use them for perception and planning. There's some of the obvious models that we tend to use in robotics here already, like CLIP and SAM. We've heard a lot about that. Hooking them up to LLMs, VLMs, like for example in SEICAN, or generative models like Rosie, or whatever Figure is doing there is of course also great. And then we've got VLAs like RT1, RT2 that Francesco mentioned earlier. And I think there's a really interesting debate to be had about whether that is a useful thing to do and in what way that becomes useful. That is not the conversation I would like to have as part of my talk right now. I would actually like to talk about sort of the emergence notion of world models that we already know about, where the idea really is that we have some form of dynamics in the world that we would like to model, where we'd like to make predictions, and ultimately we'd also like to act, though today I'm mainly going to talk about sort of predicting the world. And so a couple of prominent examples of here are, for example, the Gaia model out of Wayve, and I think that's the first one. There's already a successor of that. And I think Francesco mentioned earlier the Genie model here, which is super interesting, partly also because when we think about the notion of foundation models being pre-trained on a vast amount of data, I think Genie was pre-trained on something like 23 person-years of game data. Okay, it turns out that maybe we want to think about how we might do that in a more efficient sort of way. And by that, it's not just about the pre-training, it's actually also about the adaptation, and that is ultimately where I would like to go. There's a whole bunch of reasons why world models are really useful to us, right? So first of all, they're useful for planning. We're excited about that, right? As per the original world model paper from Harald Schmidhuber. They're actually a really useful knowledge store of agent experience, and that's quite important because it's effectively a compressed version of everything the agent has ever seen. Can be used instead of the environment. So training and imagination is super useful in a bunch of ways. One of them is of course cheap data augmentation, we've talked about in the past. Improved safety is a really big one. So if I can train an imagination, I avoid real world rollouts, and that's a useful thing to be able to do. Improved efficiency, simply because like a simulator, I mean a world model is effectively a learned simulator. Action and cost are sort of reduced, and you can use sort of compact representations of it all. And then, of course, it's a substrate for model-based RL, and model-based RL can be really quite efficient and really quite successful if we do it. And then, of course, there's counterfactual reasoning. If we have a world model that is, very rich, we can think about things that might happen if we did particular things. We're not going to get into that so much. I'll talk about some different aspects of this. I have two sort of more personal reasons that are really quite important to me in terms of why I'm excited about world models. One I'll talk about in a little while. The second one is this. So over the past decade, there's really been an emerging view of how the brain works that is sort of turns the original version of it on its head. We used to think about the fact that neuroscientists used to think about the fact that the motor cortex sort of is this control center that sort of takes in data streams and then takes action according to what it needs to do. It turns out there's actually a lot of evidence that what the neocortex does is predict what the world should be doing, and then all your actions are geared to in terms of to minimize some of discrepancy between what you think should be happening and what is actually happening. Okay, and that fits with this notion of world models really quite well. And so that is one reason why in my group we think about generative models a lot, we think about world models a lot, and some other stuff. But this is one of the reasons why I'm very keen to sort of be working in this particular area. There are a whole bunch of challenges with world models, right? So long horizon predictions remain difficult. Real world deployment is actually really hard. If you learn this sort of stuff in simulation, getting this stuff on a real robot is difficult. And we've done some work on that, which I'm not going to talk about much. The acquisition of complex scenes, real to sim, is a really important part of this problem, because ultimately, if I want to map something into my internal model, I need to figure out how to map it into my internal model so I can predict what happens next. And I'll talk about that quite a bit later. Domain shift, and this is really, really important. So new or changed environments, how do we think about robustness? How do we get efficiency of adaptation? And most of what I'll talk about later is about that. And then the specification of novel tasks. It's kind of an interesting question. And we can make some progress with that in terms of language conditioning, but it's an interesting question in a learned world model that you gathered from sort of some form of random observations, how you actually specify a task in a representation that is not directly accessible to you. And one answer might be aligned latent representations for different modalities, but that's again a different conversation. Super interesting one. The lab that I lead at Oxford, so we kind of fall into three different sort of areas that we think about, but actually it's all one. So we think about the real to sim part a lot. We've done a lot of work in the context of object-centric generative models, so object-centric representations. We do a lot in the context of representation learning. World models we've already talked about, and all of that sort of comes together in this notion of some form of applications, mainly around skill acquisition and refinement. And in the past, we've worked a lot in the context of mobile autonomy, particularly perception and sort of action prediction, mobile autonomy. This is work that at this point we did about 10 years ago, where we effectively predict the evolution of the world with a sequence-to-sequence model that is then very easily adapted to a segmentation model in a sort of 2D laser scan, but it's in an unsupervised sort of way. And a lot of the deployment work that we are undertaking in the lab is really geared towards things like small batch manufacturing, and that's something that I share with Ed, a passion for that. Small batch here is the key word, because we're thinking about things where we need to build 10 and not a million, okay? Where robots need to rapidly adapt to sort of new skills. And so we think about this also in sort of in terms of off-site construction and so on. Okay, and so with all of that in mind, I could really talk to you about how we do sim-to-real transfer for robots, where we first of all train a teacher model and then distill that into a student that then learns to operate on real-world observations, and that sort of tends to outperform everything else that was out there at the time when we first did this, I think last year, which is kind of neat. The other kind of thing that we could talk about is the language conditions or language-based goal conditioning, where we effectively use world models to do imitation learning for particular tasks, so skill acquisition from demonstrations, and then language conditioning to goals, which is kind of a cool thing, but sadly, I actually want to talk about something else. But I want to draw your attention to this because the basis for this work, which is Ditto, which is on arXiv, is actually a very cool framing of imitation learning as reinforcement learning in a learned world model with an intrinsic reward. And it turns out to work very, very, very well. And then we do a lot of work, or have done quite a bit of work in the context of world model robustness. So how do we learn a world model that actually enables robust performance across a sort of whole set of related tasks? And the way that we do that is targeted sampling of things that the policy isn't currently good at. And so that allows us to sort of formulate a maximum regret formulation for this particular sort of frame. None of that stuff I'm actually going to talk about. Instead, I'm going to talk about something totally different. Actually, I should say this. So, the real to sim part is important. I've already mentioned the object-centric generative models part. Some of my students come to me and say, hey, you used to be really interested and excited about object-centric generative models, and now it's world models. And the answer is actually it's all the same thing. And that's really, really quite important. So in the past, we've done a lot of work on representation learning, particularly unsupervised, in terms of discovering objects in 3D for things like matching, for things like scene generation and scene manipulation. But it turns out ultimately it's the same thing. And here's why. ultimately, the ability to predict the world sort of in an effective and interpretable and easily adaptable way requires the notion of a modular world model. And modular specifically is meant to say reusable, right? And composable mechanisms, right? And that's kind of interesting, right? Because ultimately also these mechanisms require that they need to operate on some form of abstractions in the input stream, right? And we might think of those as objects. And there is an interesting way of thinking about this, which I haven't really heard framed like that before, but if you think about objects as abstractions in the context of, I don't know, vision or perception, right? Then if you think about world models, which are in a dynamic world, so we're modeling dynamic systems, the equivalent abstraction is really a mechanism, right? So a question might be, first of all, how can we use the same sort of setup, the same sort of inductive biases to learn both? But also, the two of them are actually intimately related, right? Because if we have mechanisms, if we learn mechanisms that operate on perceptual abstractions, objects, and we learn these things together, or we can find a way of learning these things together, then we should actually end up with better object representations or better perceptual abstractions as we learn these modular world models. And that is sort of the big quest for us right now, kind of trying to find ways of tying these things together in a meaningful way. Okay, all right. So I've talked about the challenges of the world models. We've seen this before, but in the context of these modular world models, I really want to talk about domain shift. So robustness and efficient adaptation to novel environments. And ultimately, we'll talk about this in the context of some sequence of observations and actions. And I've already talked about why we would like a modular or flexible and interpretable model. And the point that I would like to make is, one of the hypotheses here, is that causality could actually provide the right ingredients for this. And I must admit, I'm a complete and total causality doubter. Okay, often have I wondered what is actually, what the deal is with that, which is why I work with my friend Gerhard, and we have a student in my lab that we jointly supervise, Anson Elahe, who has done a lot of the work that I'm about to talk about. And the initial brief to him was, in the context of world models, prove to me that there's actually some sense, or that we can bring causality somehow into this, because clearly that would be a useful way of thinking about mechanisms, thinking about modularity, and so on. And as I mentioned, while we talk about beautiful data sets in some of the world models that are already out there, this is the beginning of a journey, and we're going to talk about some very simple data sets until all the way at the end we actually also bring that back to a real world data set in the context of autonomous driving with the Wayve open data set. Okay, right. Let's get into the whole world models as a causal perspective. So we already talked about the fact that environment dynamics are actually made up of independent mechanisms, right? We can well imagine that. Causal dependencies tend to be sparse, and it turns out that sparsity is like the one key ingredient that we've discovered here. And so the changing in dynamics, which by the way includes actions, but the changes in dynamics can really be seen as sort of local and sparse interventions. And so discovering these causal dependencies requires a suitable representation. That's sort of the premise amongst which we work. And to make that more concrete, in a sort of very naughty example, which tends to be a very useful data set when you work in this sort of space, is sort of the particles data set where different particles interact with each other in sort of different ways. And what might an intervention look like? So here we might intervene on the yellow particle in particular that can only operate on this one particular y-axis, right? Or we might intervene in that environment on the pink particle, such that it only sort of operates on that particular, right? So that's, broadly speaking, that is the notion of intervention. So in a way, these would be sort of different, related, but intervened environments. And I told you this is part of a journey, so I'm going to talk to you about 3 proofs of concept that are sort of loosely ordered, or actually directly ordered in time evolution. 2 of them are tantalizing proofs of concept, but they really don't scale. We'll talk about that later. One of them, this latest one, isn't actually published yet. It should be published in a couple of days. So I'll show you some results that are literally sort of a few days old. But we have fairly high hopes for this because it could actually be a very, very powerful way of doing this. All right. So let's talk about the first one, which is VCD variational causal dynamics. So consider a sequence of observations and actions. We already sort of posed our main hypothesis here, which is that causal discovery requires some form of meaningful causal variables. And the question is, how do we actually get these from observations, right? Without any additional segmentation. And we can think about that by, first of all, let's start by writing down I won't show you maths, a lot of maths, but it's worth sort of dwelling on this briefly. Let's write down the generative model of the observations and the actions. Where effectively here we have an observation model, we have a policy which tells you about the actions, and we're going to ignore the policy for the purpose of this talk. And then we have a transition model. And the first conjecture is that if we think about it in a sort of with a causal inductive bias, we should end up with a representation that is more semantically meaningful because we train the representation together with the transition model. And the second conjecture really is that because we do this via these causal inductive biases, we should end up with a modular world model, which means that it should adapt efficiently by reusing stuff that it already knows about. Okay, so when I talk about all this causal thing, we're actually really talking about three paradigms that matter from the causal literature. So the first one is the independent causal mechanism hypothesis, which effectively says that there's a bunch of mechanisms, which is, you can think of that as the basis set of mechanisms that make up your dynamic system, right? And they tend to be orthogonal, so they shouldn't really overlap much. So that's the first one. Then we've got the sparse causal dependency hypothesis, which effectively says, well, every mechanism should really only act on a small subset of your state, effectively, whatever your state is. Okay. And then there's the sparse mechanism shift hypothesis that says, well, whenever you end up with an intervention, that intervention should really only affect a relatively small number of your already discovered mechanisms, because otherwise you basically end up with a completely new environment and you have to relearn everything. Okay. What do all of these things have in common? Actually, it's sparsity, and we'll see that enacted in a little while. Okay, so here's a graphical model as to how that works over k different environments. Again, we're not going to dwell on the maths much. I just want to show you about how these sort of inductive biases, or these conceptual inductive biases, map into the construction of the transition model of variation causal dynamics. So this is effectively the transition model. Independent mechanisms for each variable. Right? Whenever anybody mentions the dependence, we multiply stuff, right? So we have independent mechanisms there that we consider like that. Sparse dependencies. So what we're doing here is we're taking a latent vector. We're doing actually the same thing on both sides. We're taking the latent vector and the action, and we multiply it, Hadamard product, so dot multiply it, by a mask, effectively, that masks out stuff that shouldn't be affected by a particular mechanism. And then sparse interventions, where we effectively learn a mask that says, well, these particular mechanisms are intervened on, or these particular variables are intervened on, these are intervened on, these are not. But that's effectively how that is pushed into the transition model. And again, I'm not going to dwell on this at all. All I want to say really here is we can train this thing, hence the variational part with a variational approximation by the evidence lower bound, and we can train all of that jointly, where the sparsity in the causal graph and the sparsity in the intervention is effectively achieved by a sparsity regularization over the entire thing. That's it. But the key message here is we train the whole thing in one go, including intervention targets and everything else, from a data set of intervened environments. Okay? All right. A key property of this particular model is that we're operating directly on a latent representation. Okay? So what we're actually doing here is we get visual observations in from these intervened environments, which are these guys over there, and then what we're looking at is which part of the latent vector that comes out of that has been intervened on, and ultimately we'll also look at what the quality, the disentangled qualities of that latent vector are going to be. And when we switch this on, this is effectively the latent vector here, and here's another one, and here's another one for each one of these environments. And when we switch this on, the system believes everything's been intervened on. Why? Because everything's new. Okay, and then it goes to some training, and then it says, okay, well, this hasn't been intervened on. Everything else I can reuse across. This blue stuff has been intervened on. Everything else I can reuse. And because I've got all of these different environments, I can effectively look at all of these environments, or the system looks at all of these environments and constructs one global causal graph. So this is effectively the adjacency matrix from state and state element that says, well, this state element depends on these other state elements. And then you can map that back to a mechanism, which is nice because you can identify the mechanism. But this is effectively what that does. And it turns out that the intervention that it learns are very sensible. The global causal graph that it learns is very sensible. The next question then relates to the representation. How much of a disentanglement do we get? And this is basically what we do here. If we now look at the latent representation and we do the typical VAE thing, where we walk around one particular latent dimension and see what happens when we decode it, we can see that latent representations here, for example, tend to correspond to the x and y coordinates of particular elements, of particular objects in the scene, and so on, which is nice. It's kind of what we want in disentanglement. Whereas if we train something much more traditional, like a recurrent state space model, we don't get any of that disentanglement at all. Interestingly, it's not that VCD is better at predicting the world. It just gives you a better representation, and it is faster in terms of the adaptation. So the last part here, the faster in terms of the adaptation, we can see here, where effectively what we do is we adapt this thing with 10 rollouts, 10 observations of a previously unseen environment, and we effectively fine-tune both VCD and the RSSM version with this, and we find here that the error for VCD is much lower than the error that you would get from RSSM with the same amount of training data. Okay, and why is that? Because we have this split between stuff that we know generalizes across different environments, stuff that's been intervened on, which the interventions, where the interventions happen and what the intervention targets are, has been learned, and so you can fine-tune VCD on new observations. It will learn what needs to be intervened on, and it will only relearn those mechanisms. That's where that efficiency comes from. That's nice because it's effectively a nice proof of concept that shows that the representation is coupled to the prediction of the dynamics and all that sort of stuff. It's a super notable example in terms of data set. It gave us a lot of hope because it showcases some of the properties that we're hoping for here. But there's some fundamental issues with it. The first one is that it learns a global causal graph, and I'll say more about that in a second. And there's some challenges with this also, because some of the things that you want to model in a dynamic system are temporarily sparse. There is a chance that if I stand here for 1 million years, the ceiling will fall on my head. Do I need that in my causal model of stuff? Probably not. Okay. Also turns out that if you have one causal graph, if some of us, all of us, if some of us leave the room or more people come in, you can chuck that graph out the window. Okay, so there's some issues with that, and we will delve into that in just a second. So this first one here, VCD, learns this global causal graph. We have one mechanism per latent dimension, and at this point you go, it doesn't scale well. Correct. Very, it's a very strong inductive bias. So we want to get away from that. And the first thing that we want to do, of course, is rather than dealing with mechanisms at the latent space, at the latent element level, we really want to talk about objects and their interactions, right? So for example, the car, you have this notion that the car stops at a red light, and there's an interaction between the car and the traffic light, right? Not the individual representational elements, and so on. So we would like to model that separately from sort of other mechanisms. Now let me briefly talk about this notion of a global causal graph, okay? So it turns out we haven't come across that many people who thought about causality in the context of dynamic systems, okay? And that's really an interesting thing because it turns out that a whole bunch of standard sort of concepts go out the window, which is why we have a lot of trouble publishing this stuff amongst the causal sort of people. So anyway, consider that you have this interaction environment, right? So the entities in the scene sort of interact with each other sparsely, for example, where they touch, but they don't have to touch, some form of interaction, right? And the causal graph effectively encodes the interactions between these entities. And the causal direction is beautifully given to us because we have time, and time runs forward, and that's good. And so effectively, we want to model which objects influence which others. That's it. That's really what we're trying to do, which is sort of a global, causal discovery sort of question. And the interesting thing about that is what we see up here is effectively the same environment, just different instantiations of it. Okay, and if sort of the two entities sort of causally influence each other, there should be an edge that is induced. So every time something interacts, there's sort of an edge, and then we stash that away, which is sort of the dark gray stuff. And the challenge is that over time, we actually get something that is sort of very highly connected to all possible interactions, right? And if you were integrating that over time, what you would end up with is what people typically call the global causal graph, right? So this is what the causality community thinks of as the one true causal graph, okay? But the problem is that it's not very informative because most of the time, we may not need to model all things. Secondly, it's inflexible because we can't really adapt it to new things, to new sort of objects and causal variables or variables that we want to infer things over. And it can also be very difficult to learn because very many things are sparse, right? Or don't happen very often. And so instead what we do is we kind of learn a local causal graph. And while we thought for a little while that we were the first one who came up with this sort of concept, we were not. Turns out Animash beat us to that by about a year. But we had some nice bonding over that, which is great. But this notion here is that actually what we want is we want a flexible way of encoding which things interact at any moment in time. All right, and then we want to deal with really only those things. And we want to build that graph dynamically. Okay, that brings me to the second one, which is actually a lot simpler than the first one, as it turns out, which is commit, compete, and compose, which effectively does a very similar sort of thing, but it operates at the level of objects. And here's a disclaimer, which is also an interesting thing. Comet works at the level of having ground truth masks for the object. So it's almost like you have a slot intention or sort of an object-centric representation built on before that. And it effectively operates in two sets. Step one is discover sort of a reusable mechanism. So you get a whole bunch of intervened environments. You learn a stash of mechanisms that sort of are reusable across those environments, and that stash is fixed. And then ultimately, when you see a new environment, you compose those to make the observations fit for predictors. Okay? That's effectively what happens here. And under the hood, what this does is effectively a somewhat less beautiful search in the sense that, or brute force, in the sense that all possible combinations are considered, but only the ones who explain the world well get gradients. So that's how that works in terms of the competition and the compositionality part. And that scales slightly better. But also what we can see here is down here in the corner, we sort of indicate what particular mechanism has been employed by the ego object here, which is one of those particles. So for example here, what this is sort of it's actually a Carla simulation, but dumbed down to the point where we could make it work with the interdimensionality of our networks at the time. And what you see here is that, for example, that lead car learns that at the red traffic light it needs to slow down, so that's why it changes sort of behavior to that. One thing where this finds applicability that's sort of interesting is sort of esports and the gaming sort of community where you might say, well, actually, we want to model different behaviors of different players in sort of, I don't know, ice hockey or whatever game people might be playing, and because we can do that and decompose it, we can actually generate different players and all that sort of stuff. So that's different players with different characteristics and that sort of stuff. All right. And we find that ultimately we still see the same adaptation efficiency in the particle interactions, comet wins in the sample in the traffic domain, comet wins. In team sports, it does not. And there's a reason for that, which is another very strong inductive bias in the comet model, which is the fact that we only consider binary interactions. And it turns out in team sports, you need more than binary interactions. Okay, so that has lifted the original idea of sort of VCD from individual latent dimensions to this notion of objects. But still, it's like 2 out of 10, right? We can smell that there's something interesting happening here, but we're not quite there yet. So compared to VCD, it's better because it's effective in prediction and adaptation. It does learn a local causal graph over binary object combinations, but operates on object-centric inputs, limited binary interactions. And after learning, the mechanisms are fixed, which seems a bit nuts, right? So we want to do something about that ultimately. And that ultimately then also leads us to the last model, Spartan, which underpins this, and hopefully many of you will have thought about this already, because I've used that sort of language. Causal influence is really about learnable and sparse attention, okay? And it took us a little while to get to that point, but we did get there in the end. So here's an obvious question: why not just use a transformer for this, right? And you can. And I already said that one of the key ingredients here is sparsity. And of course, there's a whole host of sparse transformers out there, which is great. So we should just be able to use one of those. And the answer is no, we can't. And there's a reason for that. So if you look at how typically transformers are sparsified, they're sparsified typically around about at the input, where we're saying, well, we are going to let the first layer in the transformer only look at a particular context from a particular object. And that's cute, but the problem is that you get bleeding or information leaking across all the levels of all the different layers of the transformer. So by the time I get to the end, this guy here, while at the beginning only wanted to look at its immediate neighbors, for example, whatever your context is, actually gets information leaked from further away. Okay, and that is not really how we need to operate for this. And this is the stuff that should be on archive in the keyboards. So instead, Anton had a really cool idea. Actually, two really cool ideas. The first one is we can, instead of using soft attention, we can use hard attention, which effectively operates as our causal links. But this is even better because there's a way in which, instead of just looking at the connectivity of the first layer, we can actually track the number of paths that connect different tokens that exist between tokens in your input throughout the entire transformer stack. And because we can compute that, we can use it as a regularizer, which means we can train a transformer that is actually sparse and it doesn't suffer from this information leakage. But otherwise, the training objective remains the same. So predict the next step with as few connections as possible. And so here's some interesting stuff that happens. First of all, local dependency. So what you're seeing here is ground truths in sort of different environments. And then these are rollouts, but they're rollouts with different ego objects. Okay, so this guy here focuses on the blue ball, this guy here on the red, and this guy here on the green, right, and so on. And so this guy here on the blue paddle, green paddle, ball, in intervention and pong. And everything from here on is sort of imagined. And so, for example, one thing that we can see here, by the way, everything that's shaded is stuff that the system now believes is not actually relevant for what I need to predict the world. I don't care about all this stuff over here. I only care about things that might interact with me, right? So for example, and that stuff becomes non-shaded. So if you look at the real world, what happens here is the blue ball actually bounces off the wall, bounces over the green one, no actual interaction. What happens here is that the prediction of the bounce off is wrong, or is incorrect, inaccurate. But at that point, of course, you do interact with the blue ball, and the blue ball is considered important for what is required to predict the future. Here, interestingly, the blue paddle will attend to the ball when it's close to it or coming near it, and the green paddle will do the same thing. The ball hardly ever cares about where the paddles are unless it actually bounces off them. Okay, and it's this sort of structure that we get emerging from our particular sort of Spartan learning concept, and that's nice. And this is where we loop this back to something that actually becomes more real-world applicable, because one of the questions that people often ask in terms of interpretability is, if you have an autonomous driving stack, what makes the system do what it does? Okay, and by system, I literally mean some black box system. Why does it act in this sort of way? And Waymo have done a great thing, which is they actually took part of their Waymo public, Waymo open data set, and annotated it with human annotators according to what these guys believe is important for the decision making of the agent or of a human driver. What should the system actually attend to make meaningful decisions? And because we have these annotations, we can come up with this notion of, we have this blue ground truth ego vehicle, which is this guy. What you're seeing here is, I think, six predictions of 6 possible futures, which is what these sort of purple things are. So it just says, hey, in a slightly different world, I might have driven a bit faster, okay? And then you see all these shaded green things, which I hope you can see, which are shaded or alpha blended because the system does not attend to them at all. And they're green, they're true negatives in the sense that human labelers also thought they shouldn't be important. Okay? And then when you see the ones that are sort of full green, these are the ones that are also correct. Everything that's green is correct. Where the labelers and the system thought, hey, we need to look at this stuff in order to act properly. Okay? And we can see that sort of in different, not actually cherry-picked examples, but in different sort of contexts, very, very sensible things happen in terms of what the system tends to. But we can make this quantitative. So there are challenges out there where we're saying, okay, well, if we look at the Hamming distance between the learn graph and the ground truth, we can quantify how close we actually came to the learn graph, to the ground truth graph in these different environments. And so here lower is better, and it turns out that Spartan, our model, does significantly better than a whole bunch of baselines, including standard transformers, including sparse transformers, and also some other heuristics that say, okay, well, what if we only look at stuff that is near me? And another interesting thing, it's sort of interesting to wonder about what counterfactual means in the context of dynamic systems, of a dynamic system. But one way of testing this is to say, well, if I remove all of the stuff that my system believes it's not important, how does that affect my prediction of what the world does? And so here's sort of the error in this, and again, and of course you want the error to be, like the difference to be very, very little, right? Because if you remove stuff that you don't care about, your output, your prediction shouldn't change. And it turns out that Spartan is very, very faithful to that, whereas the other baselines really, really are not, apart from the global graph in intervention form. And the reason for that is that nothing really changes across different environments there, and so the global graph is actually valid across that because there's only three things, and always the same three things: the paddles and the ball. Okay, so that's cool because it scales. It's effective at prediction and adaptation. Scalable local causal graph, yes. Via sparse attention, which is nice. It still operates on an object-centric input, so that's something that we're going to fix very soon. And actually, it doesn't have a concept of a distinct mechanism yet. But there's a bunch of results that I haven't shown you, which also show that this adapts very, very quickly because we can introduce intervention tokens and work with that, and that's also how we get actions into this model. But there's only a limited amount of time. Okay, so to conclude all of that, what models need to be able to generalize and to adapt efficiently, of course, but I think the key parts here really is this notion of composable mechanisms could be able to deliver this. How do we get to composable mechanisms? Well, causality actually has some inductive biases that might be useful in this context. Across all of that, people then ask me, well, what exactly is causal about this? And the answer is actually the thinking, because the thing that makes this work is sparsity, right? That is where this comes from. In the context of dynamic systems, interestingly, we may have to rethink some of the classical sort of causal concepts when it comes to this. And one thing that I remain super excited about is the fact that learning mechanisms in dynamic systems is actually the flip side of learning sort of object abstractions in perceptual data streams. So the two are connected, and connected them will work. So that's basically it. All of that happened as part of a program grant, I should say, on embodied intelligence, which is delightful, where we look at sort of different areas, different application domains. If you're interested in social care or manufacturing in particular, let me know. But we're also active in sort of agriculture and inspection and survey. And of course, I get the pleasure and the privilege to stand here and tell you about all this stuff. But it's down to the group who do all the hard work, and in this case, particularly Anson, who's done effectively all of the causality work that I've had the pleasure to talk to you about. And that's it. All right, thanks.
Thank you so much. Great talk. Any questions? Yes.
Amazing work, really. Very foundational, I would say, very fundamental for what we're doing. I've lost a little bit. I lost along the presentation where actions do play a role, in particular how actions will influence the dynamics you learn. And in particular, the question is, what if the other agents as well, not just ego, has actions to influence the environment? Also, the others have actions that will modify their behaviors.
So it's a good point. None of the work that I've shown here actually has actions in them. That doesn't mean we can't. So we know how to do it, but right now, in the context of bringing this causality point across, it's actually very useful to talk about prediction rather than saying, oh, and now if we act, what happens then? Right? So that's the first input. So particularly when it comes to Spartan, we have a pretty good idea of how to bring them in, and also with Comet, though it's fair to say that we moved on from Comet as a stepping stone. So that's the first thing. And sorry, what was the second part of the question?
The second one is like if every agent has its own actions and preferences, as in the sports.
So the answer is we haven't had a chance yet. So we only got that working fairly recently, so we haven't had a chance yet to think about that in more depth. I often wonder about this in the context of if you observe other agents interacting with each other, whether you can actually predict enough from that. So I know that there's sort of this sort of recurrent loop that people tend to fall into, where we go, oh, but if I know what you're going to do, I might do something else, and then they might do something else, and so on. I have never really yet found that to be a significant issue in the kind of work that we've done. But I look forward to finally getting to a place where that actually might be a real issue, because I think we've achieved a lot when we get to that place.
Other questions? And actually, if I may. No, sorry. Go.
Quickly, it's a very interesting presentation, thank you. In a lot of causal models, I think having correlated inputs causes problems down the road. Did you see any ways to approach this in here? For example, what if two of your objects are connected? How can your model decide to which objects the mechanism is being applied? I don't know if you see what I mean.
Right. Okay. I think so. So we have different ways of answering that in the different models. So easiest answer is the last one, Spartan, because it doesn't yet have a sense of mechanism, which is interesting because we can still deal with interventions efficiently, even though we don't have this notion of a mechanism. But that's a different thing. So we don't have that problem in Spartan. In Comet, which is probably the most direct version of this, so the composition model does two things. It predicts which mechanism should apply, and it also predicts what the context object is. So if it turns out that two objects in Comet, if it turns out that two objects influence my ego object, then it will just pick one. It will pick the one that has a stronger influence. Does that answer your question?
I think so.
If not, we should come back.
Yeah,
All right.
very good.
All right.
Any other questions?
That's it.
Yeah.
Good.
Thanks so
All right.
much.
Thanks, guys.